Bitte heißen Sie willkommen Professor Dr. Jürgen Döllner vom Hasso Plattner Institute.
Yeah, very good morning to everyone. I guess we will have my slides. I'm Jürgen Döllner. I'm with the Hasso Plattner Institute for Digital Engineering at the University of Potsdam. I'm a software engineer, mathematician, and I like to work on to do research in the analysis, design, and construction of complex software systems, in particular related to computational geometry. Today, I will talk about a more general topic as an introduction here. It's always a good occasion to summarize a little bit my opinions and my views on how software engineering is evolving, especially in the time of generative AI. Let's start. Generative AI is something that changes software development in a fundamental way. It's not an incremental way. So it's interesting because there are signals that this might imply a kind of end of programming. Sounds weird, but I will explain it a little bit in detail what this actually means. So it's also possibly a radical change to the software development as we know it for decades, starting in the 50s when software engineering came up. We are so used to the way of we are so used to the tools, methods, and thoughts in software engineering that it's a little bit difficult to think about a different approach. It's always good to have a kind of comparison, something similar that happened before. So the printing press was something similar, compared to similar to generative AI. It, for the first time, it provided a kind of democratization of knowledge. Books, sheets of paper, whatever, could be printed in a radical new way that was not foreseen. So it's always good to see what actually happened then after inventing the first printing press by Gutenberg, for example. It created a whole new industry, and it changed completely the way, for example, books are produced. So this is a similar situation I currently do see regarding generative AI and software development. The landscape of software engineering, we all know there's a bunch of practices around, especially in the last 20 years, it became more agile, more iterative, more in a way more deeper regarding the scientific foundations, but for example, consider object orientation. In the end of 90s, consider agile development, any software methodology, consider formal languages like unified modeling languages. All this helped a lot, is helping a lot every day. But there's one key characteristics here. It's all human-based. It's human-centric. It's good for analysis, design, implementation, deployment, but always from a human-centric point of view. That is, the ingredients are basically the human logic and the way humans solve problems, also how we understand problems. We are quite limited regarding our hardware resources. And there's a kind of predominant procedural thinking. And in general, we are bound to the human dimensions in our logic, in our thinking. So this is reflected in all kind of development tools and methods. So there are some limitations, maybe many limitations. In particular, it's the scalability. If your program is a small, maybe most likely you can solve it. But as systems grow, all your methods will somehow fail. It's a proliferation of artifacts that causes this limited scalability. The complexity is increasing, especially regarding legacy code produced, generated over many, many years, time-consuming and non-deterministic development process also contribute to this, to these limitations. This is all known as the software crisis, and interestingly, it all was observed and clearly grasped intellectually 68 in a NATO conference on software, and this was a place where for the first time the expression software engineering was coined, and as well the software crisis. At this conference, and I really can recommend to read the original PDF. It's available in the internet. It's a summary of this conference. I don't know, it's about 60 pages. If you don't know that this document comes from 68, you could believe that it was written recently. Yeah. Here they recognized for the first time complexity and difficulty in software development, and this is something I used to show students when doing introduction to software engineering, that it's not a mathematical problem, it's not a formal problem, it's related to the way humans speak about problems and think about solutions, and then during typically a long process, maybe months or years, they develop technical artifacts about or for and still not really precisely defined or described situation or problem or what is the cause of the development. So the software crisis still is there, and now a little bit spoiling, there's an end of the software crisis, at least at the horizon. Yeah. Why? It's generative AI. Programming languages are languages. This explains in a very short way why large language models are so powerful. Programming languages have even a more strictly defined syntax and semantics. They are very predictable in a way, and coding standards and convention enhance the learning required for large language models. So most important, programming languages are languages. This is why we can apply the whole tool set of large language models to the domain of software engineering. Especially large language models trained on code seem to be extremely powerful, and most of you have, I'm sure, have tried several times how good the code is when you ask, for example, ChatGPT to solve something tricky. Yeah, this is one of my hobbies now. Whenever I have to wait on a bus stop, I ask ChatGPT to do something really difficult for me, and I'm always wondering how good it is. Yeah. By the way, ChatGPT regarding programming capabilities passed all the exams of my lectures. Yeah, so it's a really good tool, and we have an enormous bunch of information. We have systems like Stack Overflow or countless ticket systems industry applies. So we have a kind of synergy because structured data in our existing systems feed large language models based on sequence modeling, and so we can learn from both the code but also from the context given by natural language. There's an interesting paper, you might want to read it once you have a lot of time. It's about a cool phenomenon. It's the naturalness of software in a nutshell. Software written in some programming languages has the same characteristics like all other documents written in other, for example, natural languages. There is not a real difference because programming languages are complex, flexible, and powerful in theory, but the programs, I cite this conclusion here of the paper, that real people actually write are mostly simple and rather repetitive, and thus they have usefully predictable statistical properties. This is a key finding of years ago that explains why everything works fine. Yeah, it's the naturalness, the utterances you write down with programming languages are not very different from the utterances you apply when you talk to other people. So all this will transform the programming practices. As we know, software developers spend a large part of their time on all these typical tasks like design, coding, debugging, redesign, testing, as well as maintenance and refactoring. And in these domains we can automate. So a generative AI will shift our focus away from these traditional tasks towards specifying what a solution should do and not how to implement it. Prompts, for example, is something fundamentally new. They are meta-information that serves to derive automatically code. So it's maybe worth to, it's good to think about how can we systematically manage prompts in the future written by our experts, and based on these prompts, our systems will be produced. There's, of course, a large potential in this human-machine collaboration, a symbiosis between human insights and the speed of AI and the precision, because generative AI produces, statistically speaking, code that is much less error-prone than humans can do. The high degree of quality is impressive. It typically has learned all the best practices, and so we can reduce the likelihood of errors. And of course, the time required for doing the actual coding is neglectable in the future. Imagine that doing the implementation has not any more time budget. It's 0 seconds or 1 second, depends on how fast your data center works. So there's also a paradigm change. I call it software on demand. We are used to have a plan, to sit down with our colleagues, to have a strategic meeting, and then to work on our future software system that should solve some problem. But what if this software could automatically be generated within a controlled environment, and for a specific context? Then we could generate the software on demand, that is just in time. There would not even be a system anymore maintained and stored like today. The software would be generated only for a fraction of a second once it is needed. Exactly when a service receives a specific request, it will produce, I would even say, it will produce a corresponding software system. So there will be a decreasing need for developing general, all-encompassing software systems in advance when specific software systems can be derived at any time, at any moment. By the way, this happens with ChatGPT when you do exploratory data analysis. Just upload an Excel sheet, ask something that makes sense. What happens next? ChatGPT interprets your request, generates Python scripts using some exciting middleware system, says it always knows what to use, writes the script, executes the script on your data, receives, takes away the results, and gives you back as a download link the result file. So this software is just produced for 1 second, and you never will look at it. I sometimes do, because I'm eager to know how it works. Yeah? You can also receive, you can tell ChatGPT to give you the source code. So we have an enormous speed of efficiency. We can handle better complexity, especially when it comes to complex algorithms. Yeah? We have a kind of continuous learning, and something that still at the moment is not on the radar of most people. We will do genetic programming. That is, if we can neglect coding time, we can produce hundreds of millions of variants of a software to see which one is the best. And this is how evolution worked and works. Yeah? You just try. So this endless variety of codings to find an optimal solution will be possibly the most powerful solution strategy. We will redefine roles in software development. Software, as a traditional software engineer, maybe becomes more a strategic partner and supervisor, and we will definitely focus to an extraordinary amount on correctness and reliability checks. So this will be the central task within 10 years in software development, in my perspective. Yeah? Manual coding will decline. And we of course, we have to improve our skill sets. There's a need for oversight, for explainable AI and system design expertise, and ethics becomes an issue. Just to give you one idea about, or some ideas about how AI-adapted programming techniques and tools could look like in the future. So what will be different? We all know high-level language, we are fine. We have learned this in our studies. And it's all good for humans. Yeah, we tend to give variables good names. Yeah, because and sometimes you discuss with your colleagues about the right name. Imagine AI does not rely on that. Doesn't need a self-explaining name. So generative AI could leverage patterns and structures that are efficient for AI algorithms, but they will most likely not intuitive for humans. So this way we can optimize computational efficiency rather than the human comprehension. Also, it will allow us to produce optimized code. Maybe we will not need at all high-level programming languages anymore. You can just output machine code that is highly optimized for the specific hardware. We can even use completely different ways of generating code. For example, self-modifying code that modifies itself during execution. Yeah, this is a little bit related to genetic coding. And non-instructional code representations. For example, an enormous graph that you never will have a look at it, yeah, because you would become nervous. Maybe it's so large that you could not even see it at once, yeah, at a glance. All these are potentials that we are faced with, and I'm so eager to see how all this will work soon. For example, the ultimate risk processor, I like it because it's so cute. Imagine what instruction set do you need? And the theoretical correct answer is one instruction. It's a combined instructions, subtract, test, and jump. This is the ultimate reduced instruction set approach. With this combined instruction, you can implement everything that can be implemented. This is proven, yes, it's yet a long time ago. So this is this command stj, and it subtracts two variables, and if the first one is smaller than 0, then it jumps, otherwise it continues. Yeah, that means this machine code will not have an encoding for the instruction type. You can just skip it because there is only one instruction. Yeah? Imagine humans would not like to work with that. Yeah? Because we get crazy when we have to program based on this minimalistic instruction set. But AI can do, and AI is quite fine with that. Also, the system architecture and modularization concepts will change radically, so humans will mostly focus on the high-level architecture and the interfaces. APIs, application programming interfaces, become the critical aspects in an AI or generative AI system, because this is subject of an explicit, basically strategic, sometimes political design. For that reason, humans will concentrate on these parts rather than on how to implement modules. Modules below a certain complexity are best candidates for being generated automatically. This is done, for example, by software analysis. It can scan your system and then give you a first roadmap towards what modules should be first candidates for being replaced by generative solutions. And other modules, interestingly, this is my current research, it's related to current research in my group, you can sometimes replace complete subsystems by a black box, and inside this black box there is a large language model or a multi-model large language model. So your system partially will use modules that are just trained black boxes. You never look inside, but it works. So it's also a critical aspect, yeah, of course, yeah, because we are how to make sure that it does what it is supposed to do. But this is a fundamental change as well, so we can collapse sometimes the implementation of systems into these boxes. And we should have a certain kind of attention. Yeah, we should be very aware of these radical changes, because sometimes change appears, yeah, on the sky, and you don't realize that this is a change, yeah, and it's maybe a radical change. Yeah, this is the last slide. Thank you for your attention.
Thank you, Professor Dr. Jürgen Döllner of HPI.